Rich Sutton and Andy Bartow. So this book is considered the seminal textbook for reinforcement learning. It's actually available. The seminal textbook for reinforcement learning. It's actually available free online, and in fact Rich Sutton is currently working on a second edition to the book, which is also available online in its current draft. We'll be using actually the notation from the second edition in this class. If you just want to be compatible and understand exactly by comparing between them, that's probably the one to look at. So this is a really good choice. However, some people prefer something a bit more concise. This one is maybe 400 pages and very readable, but it's also, gives you a good overview and sense of the big ideas of reinforcement learning at a sort of intuitive level. However, some people prefer a more rigorous sort of mathematical textbook, and so the one which I'd recommend if you're one of those type of people is by Csaba Szepesvári. It's called Algorithms for Reinforcement Learning. This is a much shorter textbook. It's less than 100 pages, covers all the main ideas very concisely, much more sort of terse style. But you'll get less of the intuition, but more of the rigor, and you'll really get the sort of, for those of you who prefer the theoretical side, I find that this is what some people actually prefer reading. But the style of this course will be somewhat closer to the first textbook. Okay. So let's start by trying to understand reinforcement learning and get some idea of, what is this thing we're all sitting here to try and learn about and talk about. So to begin with, let's try and sort of place it within the whole field of science. And I think one of the special things about reinforcement learning is that it sort of sits at the intersection of many different fields of science. So we have here in the middle of this sort of Venn diagram, we've got reinforcement learning, and what this is supposed to illustrate is the fact that for many of these different fields of endeavour, there is a branch of that field which actually is trying to study the same problem that we're going to talk about in reinforcement learning. So what is that problem? It's essentially the science of decision making. I think that's what makes it so general and so interesting across many, many different fields. It's a fundamental science. It's trying to understand the optimal way to make decisions. And so this comes up again and again. So in computer science, we study this under the umbrella of machine learning, and specifically reinforcement learning, and that's what we'll look at in this course. But if you go to engineering and talk to people in the engineering world, they have a large part of engineering devoted to what's called optimal control, which essentially is studying the same type of problems with many of the same methods under different names, which is, in other words, how to optimally decide a sequence of actions so as to get the best results at the end of the day. In neuroscience, it turns out that one of the major discoveries in neuroscience in the last couple of decades is actually an understanding of how the human brain actually is believed to make decisions, and that a large part of the human brain is devoted to what's called the dopamine system, and this neurotransmitter dopamine actually exactly reflects one of the main algorithms which we'll study in this course. And so the reward system of the human brain is really studied widely and a major part of neuroscience now, and it's really people there are trying to understand exactly the reinforcement learning methods that we'll talk about in this course, and it's believed to underlie human decision making as well. Again, in psychology, there's been a lot of work going back to Skinner and so forth on classical conditioning and operant conditioning, which again is trying to understand how animals make decisions, how and why animal behavior occurs. If you give them some rewards and you see that this animal start to salivate, the theory that underlies that is essentially reinforcement learning again. In mathematics, there's again an equivalent to reinforcement learning, studying the maths of optimal control again, and it's known as operations research. And finally, in economics, there's the fields of game theory and utility theory and bounded rationality, and these are all, again, getting the same questions of how and why people make decisions if they're trying to optimize their utility. So really, it's something fundamental, and I think it's something of general interest in many different areas. So if we zoom in a bit to this diagram and try to understand, in this course we're going to talk about reinforcement learning. So there's a few things which differentiate reinforcement learning from supervised learning and from unsupervised learning as well. And so let's just see if we can understand those distinctions. So the first one is maybe the most obvious, that there's no supervisor. When we do reinforcement learning, no one tells us the right action to take. Instead, it's a trial and error paradigm. There's no supervisor. There's just this reward signal saying, that was good, or that was bad, or that was worth 3 points, or that was worth minus 10 points. No one actually says that was the best thing to do that action in this situation. So there's no supervisor. The second major distinction is that when you get that feedback saying good or bad, it doesn't come instantaneously. It may be delayed by many steps. So in the reinforcement learning paradigm, you make a decision now, and it may be many, many steps later that you actually see whether that was a good decision or a bad decision as the kind of the decisions that you may unfold over time, and it may be that it's only retrospectively that you realize that was a bad decision, because at the time it looked like it was very good, and maybe even you got positive rewards for several steps before some catastrophic large negative reward. So in RL, the feedback is delayed, and that makes it very different again. Furthermore, time really matters in RL. So we're talking about sequential processes, sequential decision-making processes, where one step after another, the agent gets to make decisions, pick actions, see how much reward the agent gets, and then optimize those rewards to get the best possible outcomes. So we're not talking about IID data here. We're not talking about the classical supervised or unsupervised learning settings where you get some IID data set and you just get to learn on that data set. Here, we've got a dynamic system. There's an agent moving through a world. And imagine a robot sitting, walking through some environment. What that robot sees at 1 second is going to be very correlated to what it sees at the next second. This doesn't really, the IID paradigm that we're familiar with doesn't apply to RL. And specifically, perhaps the most important way in which IID breaks down is that in reinforcement learning, the agent gets to take actions. It gets to influence its environment. It gets to move around. Imagine this robot. It gets to move around in its robot. If I'm in the robot and I walk to this side of the room, I will receive very different data. So I'll see different things. I'll get different rewards to if I'd moved over to this side of the room. So the agent is actually influencing the data that it sees. This is like an active learning process. So it basically got this combined set of differences that defines the RL paradigm and makes it quite distinct. But in many ways, this is really the paradigm that's faced by all of those fields of science we just talked about when we try to understand what it really means to optimize a sequence of decisions. Okay, so let's try and make this concrete by talking about some examples of what would be our reinforcement learning problems. Let's not talk in the abstract. Let's get a feel of what RL is all about. So I'm just going to kind of illustrate this with a few examples, and then we'll have a couple of videos. This is the first lecture. It's nice to have a bit of fun. And so one example would be flying stunt maneuvers in a helicopter. We'll see a video in just a second. So here, that you've got a helicopter being controlled. You want this helicopter to make a particular maneuver. It's not that anyone tells you at any given moment, yes, you've done the right thing, or no, you've done the wrong thing. It's that at the end of some period of time, you want to have executed this maneuver, and maybe someone says good or bad at the end of it. And crashing is typically very bad. Video. So let's faced by all of those fields of science we just talked about when we try to understand what it really means to optimize a sequence of decisions. Okay, so let's try and make this concrete by talking about some examples of what would be our reinforcement learning problems. Let's not talk in the abstract. Let's get a feel of what RL is all about. So I'm just going to kind of illustrate this with a few examples, and then we'll have a couple of videos. This is the first lecture. It's nice to have a bit of fun. And so one example would be flying stunt maneuvers in a helicopter. We'll see a video in just a second. So here, that you've got a helicopter being controlled. You want this helicopter to make a particular maneuver. It's not that anyone tells you at any given moment, yes, you've done the right thing, or no, you've done the wrong thing. It's that at the end of some period of time, you want to have executed this maneuver, and maybe someone says good or bad at the end of it. And crashing is typically very bad. Another example would be to play the game of backgammon. And one of the famous successes of reinforcement learning is when Jerry Tassaro defeated the world human champion at the game of backgammon, just by reinforcement learning. So this is a system that was basically playing the game again and again, and just by trial and error learning, figured out a way to play backgammon better than humans. Another example would be to manage an investment portfolio, where now the time steps are decisions which are being made perhaps in real time. Perhaps there's some stream of data coming in this trading agent, and it has to make decisions about what to invest where and in what products, and the reward in this case might be money, and it's trying to maximize the amount that it makes over time. But it's a clear example of a reinforcement learning strategy, a reinforcement learning problem. Or to control a power station. A power station is a an RL problem in the sense that there's a sequence of controls that you can make of that power station. Perhaps the controls are, it could be the torques on the motors of how things are being converted. It could be different ratios that are controlling the batteries and so forth. There's all kinds of different tweaks. In a wind turbine, you have the blade pitches and so forth. There's all kinds of different parameters which can be controlled at every second so as to optimize the throughput of this power station. So there are many different decisions that can be made there over time, and there's some long-term goal, which is efficient generation. Another example would be to make a humanoid robot walk. So you don't want this thing to fall over, you maybe want it to get to the other side of the room. How do you do that? This is a reinforcement learning problem. There's rewards at every step telling you whether it's falling over or whether it's making progress. And at every step it's got to learn for itself how to figure out this behavior of walking across the room. Finally, this is an example from DeepMind where we've been working on this recently. How do you get a single program to play against a suite of different games? So you just sit down in front of an Atari emulator. You want to play this Atari game, say Better Than a Human. How do you do that if you just sit down, watch a stream of video coming in and get to control the joystick? How do you learn how to play that game to some good level and get the maximum amount of score on that game? Okay, so let's have some videos just to make this a little bit concrete. So each of those examples I just gave, I should add as a real successes of reinforcement learning. So they weren't just abstract examples. They're things where reinforcement learning agents have been successfully built to solve each of these problems. So this is a nice example of the helicopter. So it's not a full-size helicopter. It's a fairly substantial model helicopter. So when it crashes, it doesn't cost like $1 million. But it's learned through reinforcement learning to perform particular stunt maneuvers, which are described down in the bottom right there. And it's being asked now to kind of show off and execute all of these behaviors that it's learned, essentially through trial and error. Basically, this thing learned by accumulating experience, learning from that experience, being told, a reward function of what's good and what's bad, and then executing that behavior to see all of these different maneuvers now. Some of them are quite fun. And believe me, if you just take a model helicopter and try to control it yourself, it's very hard to make it fly upside down, or to do a split S, or to do some of these maneuvers. Okay.
Were they trained manually? Were they simulated? Did the training runs by simulation, or it was in real time, just reflying?
So the way this was done, they built a model. They learned to model. So we'll come to this later in the course. They built a model first.
Simulated? Did the training runs by simulation, or it was in real time, just reflying?
So the way this was done, they built a model. They learned to model. So we'll come to this later in the course. They built a model first. Once they had a model of how the helicopter behaves, they then did some planning with respect to the model, and they were able to actually then, so the learning was done on the model offline and then applied to so the model was learned from real data, and then it was able to learn with respect to that model how to perform optimally. Just want to show one more. So this is an example of something we've been working on. This is the agent which plays the Atari games against... so this is basically a system which is learning by trial and error. It doesn't know anything about each of these games. These are all different Atari games, for those of you who are familiar with the classic Atari console. And all it's shown is basically this video we're seeing here, and it gets to control the joystick, and it's told how much score it gets. And it basically has to learn to figure out how to play the game with no knowledge. No one tells it the rules of the game or what's going to happen. It just figures out how to play very well and maximize its score through reinforcement learning. And you can see the games are very different. This is a side-scrolling game where you have to kind of blow up all of these things and accumulates score by shooting stuff and moving along. Some of them are sort of pseudo 3D, like this Battle Zone is like a pseudo 3D game. We don't claim these are good games, by the way, just that we build a reinforcement learning agent to be able to play them all, and it learns to do better than humans in more than half of the games that we played against. This is a really ridiculous game where the game is literally to make a chicken cross the road, and it learns to do that. This is more of a classic kind of shoot-'em-up Space Invaders type game called Demon Attack. Learns to kind of duck in and out of the bullets and shoot all the aliens. This one is Pong, the classic original Atari game, and we're controlling the green guy here and basically learning to hit it right. You have to get these like sharp angles off the corner to be able to get it past the opponent, and it sort of learns this strategy and eventually learns a perfect strategy of winning every game. Yes?
You're allowing, presumably, the reinforcement algorithm to respond to stimuli in a much shorter space of time than a human would be able to do that. Simply because of the hand-eye coordination, for example, there must be a lower.
Actually, no. We tried to match it to roughly human. So we
time than a human would be able to do that. Simply because of the hand-eye coordination, for example, there must be a lower.
Actually, no. We tried to match it to roughly human. So we've made decisions at 15 hertz, which is not way beyond what humans are capable of. So
it's a fair.
I think it's reasonably fair. Yeah. So this game is Sequest. Here you'll notice it has to do like delayed decision making. Like it has to go up to the top, fill up with fuel, which doesn't get it any score, so that then it can go back and shoot agent, all these different monsters and things, and fish and sharks, and go back and get more score. Here it has to jump around this whole grid, turn everything yellow whilst avoiding this coily thing here. It can use this little teleport thing, and the goal has to figure out just from these raw joystick maneuvers how to kind of fill up the whole screen and get this big score at the end by doing that. And again, we haven't told it anything about these different games. It's just figured out what to do just by trial and error on the joystick. This game's kind of weird. It has to sort of sweep this thing around and get the liars whilst avoiding the things which will kill it. This one, I guess, probably familiar with, Space Invaders. We've got this agent that's being controlled, and it learns this very human-like strategy. First of all, it captures the mothership. Also learns a very human-like strategy of doing things a column at a time, which gives it more time as the game speeds up. It takes longer for the aliens to move from one side of the screen to the other and move down, and that actually gives it more time to be able to sweep up and kill them all, and it figures out that strategy for itself. This game, boxing, again, a little bit of a strange Atari game. I don't think racial stereotypes are intended with this one, but anyway, so we're controlling this one on the left and learning this strategy of pummeling this other guy into the corner there. Right, so a real variety of different games there.
How long does it take to train this algorithm, and were there any ones that were particularly tricky to train?
So yes, it
just off a MacBook, for instance.
Yeah. So on a MacBook it would take quite a while. We use it on a GPU.
Yeah.
So using deep learning. So there's a whole story there of exactly what we do. but roughly speaking, it takes around 3 or 4 days of training to get to the human level of performance on each game per game. So 3 or 4 days of compute time to do that. Okay, so that hopefully gives a flavour of what RL is about. And I don't want you to think that RL is just about games, but actually a lot of my background in reinforcement learning has been on applying reinforcement learning to games, to board games, to video games, and I think they're kind of fun to talk about. So, some of the examples will be drawn from my experience, and so I really want you to see this as just examples of how RL can be applied, and in that sense, games are just like little microcosms of real things which happen in the real world, which have very clearly defined rules and help us to understand how these ideas can be applied. So don't think it's just a game-specific idea, it's very generally applicable. Okay, so let's talk now about the reinforcement learning problem. So any questions first about, before we move on? I think we'll start to get into more details and understand things a bit more clearly in just a second. Yeah?
Just on the Atari games thing, do you use what it learns on one game and then sort of transfer that knowledge to a different game, or is it starting fresh each time?
It starts fresh each time.
Right.
Okay, so the RL problem. So one of the most fundamental quantities in reinforcement learning we're just going to talk about in a bit more detail now, and this is the idea of rewards. So a reward, what is it? Well, it's just a number. It's a scalar feedback signal, this random variable RT. So every time step t, we're going to define this feedback signal RT, saying basically how well is the agent doing at that time step. And the job of the agent is basically to get as many, to sum up these RTs and get as much reward as possible in total. That's what the agent's goal is. And so, is this really a good way to understand what we mean by goals? Does this cover what we mean by goals in all kinds of different problems? Well, what we follow in reinforcement learning is kind of based on the following premise, which is a hypothesis, if you like, informally, which is that all goals can be described by the maximization of expected cumulative reward. So there's nothing that we mean by goal following which can't be described by some scalar feedback signal and the maximization of that feedback signal over time into the future. So, that's a little bit controversial. So you should think about cumulative reward. So there's nothing that we mean by goal following which can't be described by some scalar feedback signal and the maximization of that feedback signal over time into the future. So, that's a little bit controversial. So you should think about that. Do you agree with it? What do people think? Is this something you agree with? We're certainly going to be following that and using that as the premise for the remainder of the course. But it's okay if you've got, in the back of your mind, well, really? Can you do this, this, or this? So just have a think about that for a second. Any thoughts? Do people object? Are they happy? I'll take silence as happiness.
Just at the end of the game. There's no intermediate reward. How would you wouldn't be able to use reinforcement learning where that was the case, would you?
So intermediate rewards are fine? Or
no intermediate rewards. It's all at the end. So
okay.
You don't know anything until you get to the end.
That's absolutely fine. So that just means that we're defining the goal then. So if there's no intermediate rewards, is the question, what happens? And then in that case, what we define is that we define an end of episode, and we define a reward at the end of the episode. And now the sum of the rewards is exactly how well you do at the end of that episode, and the goal of the agent is to pick action. So the sum of the rewards is exactly how well you do at the end of that episode, and the goal of the agent is to pick action so as to maximize that expected sum of rewards at the end of the sum of the rewards is exactly how well you do at the end of that episode, and the goal of the agent is to pick action so as to maximize that expected sum of rewards at the end of the episode.
So what if the goal is, say, to pass some sort of challenge within the shortest amount of time? So it's...
Okay, so the question was, what about if it's a time-based goal, like if the goal is to try and do something in the shortest amount of time? So typically what we do there is we define the reward signal to be -1 per time step. And then again, there's a termination of the episode at the end of when you actually achieve your goal, you stop. And now it's a well-defined objective to maximize your cumulative reward, basically minimizes the time that it takes to reach goal. So let's actually make this concrete again by talking about some different rewards. So let's actually look at the examples we used. So we started by talking about the stunt maneuvers in a helicopter. So we have, in that case, the rewards might take the following form of a positive reward each time we follow the desired trajectory or come within some epsilon radius of where we want to be, and a large negative reward for crashing. really crashing should be bad. It should learn to not do that. If we're playing a game like backgammon, there would be 0 intermediate rewards to follow the question, but at the end of the game, we would give a signal saying, if you won the game, that's good. If you lost the game, bad. And then the agent just figures out for itself how to maximize those rewards, and it will learn to take decisions along the way that will maximize at the end of the game how well it does. If you're managing an investment portfolio, I guess one of the good things about finance has a very clear reward signal, which is dollars or pounds, and so in that case, the goal is simply to maximize the total reward. Controlling a power station, there would typically be some positive reward for each unit of power that's produced by this power station. But there might also be negative rewards for exceeding safety thresholds or doing something which is not, maybe there's regulations by the regulator which have to be respected. And if you want to make a robot walk, you might have a positive reward for forward motion. Each unit of distance that you travel might perhaps give a unit of reward. And there might be, again, a large negative reward for falling over. So each of these examples of problems where they're very different problems. They might not feel at first glance like there's a common framework for all of these, but our goal is going to be to build a unifying framework where within machine learning we can address all of these different types of problems within the same formalism and therefore solve them all using the same agents and the same. Our goal is going to be to build a unifying framework where within machine learning we can address all of these different types of problems within the same formalism and therefore solve them all using the same agents and the same ideas. And so the first step is understanding the reward signal. We get reward at every time step. Okay. And in the Atari example, finally, in that case, we just gave positive or negative reward for each change in score at every step. Like if you got 10 more points. points in that step, it'll be a plus 10 reward at that time step. Okay, so now what is this framework? You should be asking yourself, well, these are all really very different problems. How can we even imagine a unifying framework for all of them? And so, we think of this as sequential decision making, and the goal in each case is the same. That's what unifies them together. But the goal is to select actions so as to maximize the total future reward. But how can we even imagine score at every step? Like if you got 10 more points in that step, it'd be a plus 10 reward at that time step. Okay, so now what is this framework? You should be asking yourself, well, these are all really very different problems. How can we even imagine a unifying framework for all of them? And so, we think of this as sequential decision making, and the goal in each case is the same. That's what unifies them together. But the goal is to select actions so as to maximize the total future reward. We basically want to pick a sequence of actions so that we get the best results, the most total reward along our trajectory. And in particular, we need to note that what that means is that we have to plan ahead. We have to think ahead, because actions may have long-term consequences, and the reward that we get might not come now. It might come at some future step. And sometimes that might even mean that you have to kind of give up some good reward now so as to get more reward later. So you can't be greedy when you do reinforcement learning. You have to think ahead. And examples of that would be, like a financial investment where you have to spend some money now, which so you're losing money. You spend some money, but then you believe that later you'll get more money back once this matures. Or if you're in the helicopter example, maybe it's running low on fuel. So you might want to stop, lose some reward for following your maneuvers to refuel for a while. But that might prevent a crash in several hours' time and therefore actually lead to longer runs and more reward in the long run. Or if you're playing a game of backgammon or chess or something, you might want to choose a move which doesn't look like it's going to make you immediate gains. You don't take the opponent's queen, but instead you do some strategic thing which helps you much later on, because you think that blocking your opponent now might help you do better later on in the game. Okay, so the formalism we're going to use, we're just going to develop that a little bit in terms of this interaction between agents and environments. So I'm going to use this big brain thing here to represent the agent. So this is the thing which we are controlling. Our goal is to build this brain. We want to build an algorithm which is going to sit inside the brain of something we're going to call the agent. And that thing is going to be responsible for taking actions. Like it's able to take actions like deciding what the torques are going to be on the motor for controlling the robot, or deciding what investments to make or what moves to play. Those are the actions that our algorithm, our agent, is able to make. And at each step, those actions are taken based on information that it's receiving. So every step, it basically gets to see something of the world. Like it might be a robot with a camera, and it gets to see a snapshot of what's happening at that time in the world. And it gets some reward signal. This is our reward that we've just discussed, saying how well it's doing at that step. And that's it. That's all the agent sees. It gets the observation coming in, reward coming in, has to make a decision. So that's our goal, is to figure out algorithms that sit in this brain here. On the other side of the fence, we have an environment. So I'm going to represent the environment by this sort of world. This is what's out there on the other side of the agent, the thing it's interacting with. And what's going to happen is there's this loop over time. You can think of it as a loop where the agent is interacting with the environment, and every step it's seeing something of the world. It gets some observation where it's seeing a snapshot of the world at this moment. The agent's wandering around seeing stuff. And the environment is generating what that observation will be and what the reward is. So if you imagine this is the Atari environment or something, then there's some actual real Atari game that's generating the next observation, the next screen, and the score. But we're not controlling that part. We have no control over the environment except through this channel here. We get to influence the environment solely by the actions that we take within that environment. So the agent influences the environment by taking actions within it. A robot can move around and influence it where it is within the environment or where objects are, and so forth. Okay? So an interaction between agent and environment. And this just goes on, and the trial and error loop that we define for reinforcement learning is basically a time series of observations, rewards, and actions, and that time series defines the experience of the agent. And that experience is the data that we use for reinforcement learning. So the machine learning problem of RL is concerned with this source of data, this stream of data coming through, observations, actions, rewards.
We always limit ourselves to just strictly a scalar reward. Because, for example, I can imagine interacting with a world and I make a decision that, increases my standing with my boss but pisses off my girlfriend, for example, and I might,
Good. Okay, so the question was, do we have to example observations, actions, rewards?
We always limit ourselves to just strictly a scalar reward. Because, for example, I can imagine interacting with a world and I make a decision that, increases my standing with my boss but pisses off my girlfriend, for example, and I might,
Good. Okay, so the question was, do we have to limit ourselves to a scalar reward? So I thought people were suspiciously silent. So let's go back to this hypothesis. So the reward hypothesis was that the reward is a single scalar feedback signal, and a scalar feedback signal is sufficient to describe everything we mean by goals. So the question is, well, sometimes there are maybe different conflicting goals that you might have, and how do you